Perfect. Go ahead.
Perfect. So, well, hi everyone. I'm really honored to be invited here at the symposium. And today I will try to take my PhD work on interpretability of deep learning for the classification of medical images and summarize it in less than 10 slides. And obviously, I will mostly talk about pathology images today. So the work was done under the supervision of Professor Stéphane Marchand-Maillet from the University of Geneva, Henning Müller from the University of Geneva and HSSO. And this work was also funded by 3 European projects in the Horizon 2020 framework for research and innovation that are Process, XMode, and AI for Media. So the outline of the 10 slides is the following. I would like to focus really on the overall goal of this work and the bigger picture. So the amount of technical detail will be slightly reduced, but please feel free to really reach out to me afterwards or anytime, contact me by email if you really want to know the details about the rest of the work. I will introduce the context, so the motivation behind my work, the definition of interpretability that I will refer to during this presentation, and then I will focus on research questions, state of the art. But I think the most important slides are really 5, 6, and 7, and 8, where there is really the contribution that I am proposing in the thesis. And afterwards, I would look a bit into strengths and limitations of this work. So I'm interested in taking a look at the broader perspective from the machine learning and information theory viewpoint. So please allow me to take a step back from pathology applications for a second and to place the motivation behind my interest for this work at the higher level, reflecting thoughts that are also shared and largely discussed within the machine learning community. Within the past decades, the availability of annotated data has grown exponentially and has been followed by the physical improvement of computational possibilities. So with the computing resources that we have available now, we can train complex deep learning models with billions of parameters in a few hours, and that's awesome. But these models benefit from the availability of large data sets, and they're like, as other machine learning models, they are anyways approximations of the true underlying phenomenon that we're analyzing. And these approximations, as George Box said a long time ago, are never exactly true. So there were several proofs in the literature that deep learning models not always predict outcomes as we would expect, despite their impeccable performance on testing data. And I think here what I want to point is that the evaluation of these models by their sole test performance is actually insufficient, and we should drive the development towards building accurate and reliable models at the same time at the place of solely accurate models. So we need to keep into account accuracy, obviously, but we also want reliability. And reliability is given by multiple desiderable factors, including the ability to generalize, to justify decision-making, and eventually to show improvements of trust upon sustained use. So what I think we need to do here, in fact, is to stop evaluating models by the sole test performance and build AI systems around the needs of physicians. And to do so, we need to provide interpretability to better understand what the model is doing and when it is expected to fail. Now, I mentioned interpretability. I think it's important to define what I mean here. So the definition that I'm showing in the slides here is taken from the work of Torchiveles and Kim that define interpretability as follows. So given an AI system, interpretability is what makes its output generation process understandable and explainable to humans. And we need to keep in mind that not all humans that will be working with this are necessarily familiar with machine learning and the meaning of optimization landscape, for example, of neural networks. So we can try to find interpretability through iterations in multiple forms. We can provide visualizations, text, tabular data, and we can try to introduce it directly in the design of our models, or we can take a model that was working before and introduce interpretability analysis in a post-hoc way to improve the understandability of how this outcome was reached by the model. And in theory, there is still no clear definition for interpretability. So there is a lot of discussion also in the field about this. But I think this is a good starting point for us today. And the machine learning literature obviously has seen an explosion of papers concerning this topic. And most of the methods that are applied to healthcare are actually postdocs. So they are performed on already trained models. And I think the reason for this is that post-hoc interpretability methods do not require any other training iteration. So they're essentially cheap in terms of the parameters that need to be learned for this additional task. And the performance of the regional model is kept untouched. So they can be used on already existing methods without altering their performance. And the existing work on histology focuses mostly on two approaches that are gradient-weighted class activation mapping and local interpretable model agnostic methods. Now, some of the observed results here is that the heat maps generated strongly depend on the architecture that is being interpreted and often are too blurred and difficult to understand. And there is this work by Ian Palatnik that's shown that essentially explanations might perform much better, meaning that they would give much more meaningful and understandable explanations if some regions were selected ad hoc to train the surrogate model that is generating the explanation, so to obtain the explanations. And so another important point is the reliability of the explanations that we are observing at, and making sure that we don't generate explanations that are just tricking us into believing more in the model. So on the basis of all of these, the focus of the research question in this work is whether we can make deep learning models for medical image classification understandable to physicians, and how can these analyses be used to improve model generalization to have better models. And the first contribution here is called sharp line, and the specific problem that I addressed is that of this blur aspect that heat maps have, and that often they are unreliable in the sense that if you generate multiple times the explanation for the same model for the same input, you would get very different explanations. And the idea here is to essentially use nuclei entities as inputs to the LIME algorithm, rather than having a supervised superpixel selection that is in the base LIME algorithm. And we evaluated this both qualitatively and quantitatively. We interacted with experts to get some feedback. And I think that the majority of experts replied that SharpLime was the easiest to understand. But most importantly, what they did for us is that they suggested us important direction for future improvements. So there is a big clarification that emerged here that is what I call a lost in translation phenomenon. So the experts would actually expect explanations at the level of the entire image, even though this did not correspond exactly to how this model in particular that was being interpreted was working, because the model was really looking at high magnification patches. So we have this loss in translation where the expert would expect some kind of explanation that represents a behavior that is close to him, but the model is actually doing something different. So we cannot generate explanation for what the model is not doing. And so another contribution that I proposed is wanted to address the fact that even if we are able to look with heat maps where the network is looking at, it is difficult to abstract what in these activated regions is actually meaningful to the model, if it is some nuclei, if it is the background, if it is some stroma or something like that. So the idea here is to generate user-friendly explanations that are expressed in terms of clinical concepts such as nuclear morphology. So as Guillaume previously was showing, we see that in tumorous images, the nuclei size, for example, is larger. And there are also modifications in terms of texture and appearance of the nuclei. And what I'm showing here is an example of explanations where we can quantify essentially up to what point the model prediction would be changed if some of these interpretable features, for example, nuclei area, were modified. So if we were to increase the area of the nuclei in these images, we would expect, for example, a higher probability of seeing the model assigning tumor to that image. And this is one of the important points of these contributions. Then, as I mentioned before, another objective that I had was not only understanding existing models, but also showing that we can use this knowledge to generate better and more accurate models, to see where the models that we have are failing, and how we can improve and correct for those failures. So I don't think we have enough time to go into details here, but in concrete, what I did was using regression concept vectors to quantify how much information about a given feature we can identify across deep learning layers. And on the basis of this information, we can prune off some of those layers that are learning features that we don't want to have. And this seems to improve, for example, the transfer to some histopathology tasks. And finally, I think that this idea of pruning can be generalized to the idea of actually having a model that we can guide, for which we can drive the training process, and that we can guide to focus on desired features or desired concept, and that we can guide to forget instead other undesired ones. So, for example, we might have this CNN classifier that is ideally focusing on learning meaningful features about the nuclei, such as appearance, density, nuclei size, but that would be forgetting, so discarding these staining differences among multiple institutions. And this guidance can be obtained by leveraging an inductive bias that can be created by combining multitask learning and adversarial training. And one thing that I like to say about the results in here is that the model seems to be more robust and that generalizes better to unseen data. So just to summarize here, I think that the strengths of this work are that we contributed, and I contributed on how we can explain deep learning models. And we did this by a user-centric approach. So putting the physician really in the center and trying to imagine and to understand what might be the needs and the requirements in this case. And this helps us to generate new insights actually on deep learning mechanisms. So according to my results, CNNs seem to be paying more attention to the nuclei than the background in this histopathology images. And that actually there is some bias towards texture that is inherited from pre-training on ImageNet, and it is maintained also after fine-tuning on the histopathology images. But this bias might be corrected, for example, with guiding the CNN network to learn nuclei counts with the multitask adversarial architecture that I proposed before. And obviously, this work has still limitations. One of the points is that it is very much scale dependent. So all the concepts that I've been using and all the observations I've been using were done at 40x, and probably different concepts and different conclusions would be done at a different magnification. And yeah, this is the end of my talk. And if there are questions, I'll be happy to answer afterwards.
Thank you, Mara, for diving into the problem of interpretability and taking trying to understand it from the MD's perspective.